here's less homework. I'm starting to like up my expectations on the homework. You might notice on that one too. So I'm going to be expecting more writing, more explanation, completeness. Any questions on any of that stuff, let me know. And if you want to talk about it after class too, maybe that's even a good idea if you're uncertain about what I'm talking about, what I want. We got no class Monday, right?
Correct.
Okay, I was like, oh, I was like excited because I always love to tell people that when they don't know it, because it's a blissful thing.
I think about it there for a minute. I was like, why don't we have class on Monday?
Cause fuck class.
That's what I'm saying.
Yeah. So let's see. So got one more assignment. This is due next Friday, so that we can chat about it on Wednesday. Due to the no class. This is homework. God, I don't know, 5. Sure.
Yeah.
Sure. 5 plus or minus 1. 20. These are clearly not in order. Well, no, wait, they are now. Look at that. This is a little bit longer than the short ones I've been given, but you got a little extra time, and these are kind of shorter problems too. I think they're a little more computational. I tried to avoid suffering, us suffering, you suffering, mostly.
Just chapter 4.
Yes, ma'am. Yeah. And that's our last chapter 4. And then if you have time, you probably have time, if you feel the motivation, start reading chapter 5. That would help you on next Wednesday for sure. We are not going anywhere close to what the schedule is. I don't know if you've looked at the schedule the way I planned it out. I think we were going to be done with like this stuff the first like 4 weeks or something. The good news is that there's no class after this one that expects you to like know certain things. So we're just gonna like go and learn and make sure we understand what we get through. Seems like a better plan to me than just cramming through and like hoping you get something out of it. I think some classes go that way. I don't really think that makes much sense. In calc, that makes sense, but that's about it around here. So start reading chapter 5. Any musicians here? Musician? Instrument play? What do you play? Violin. Oh, nice. What do you play, Diana? Guitar. Awesome. I've been playing guitar for like my whole life and didn't really learn anything about music theory until I became a bassist for a band here on campus that luckily none of you got to see. Yeah, so being a bassist made me need to understand things. I really needed to understand how notes related, how chords were created. Maybe Trinity can actually help with this. I might cheat. You know what I'm drawing, don't you? Circle of fifths. So let's take a look at that. I'm just going to cheat. Yeah, C, G. And you don't even need to write this down. This is just like, I wanted to kind of relate some of the stuff we've been talking about. This is a super shitty one too. Oh my god, it's so poorly planned. So flat G, D, flat E. These are flats here, and then okay, all right, it's not too bad. Flat B. The planning wasn't terrible. Flat F. Or not F, flat F, just F. Yeah. Flat F would be an E. Yeah. So, you know the musical scale, right? A, B, C. Are you vaguely familiar with this? Anything about music at all? Yeah, a little bit. Kyle?
No.
No. Okay. Cool. No worries. So we've got these main notes, and then there's some flats and sharps in here. So all in all, there's like 12 tones in the Western scale. And so you break up a thing called an octave into these 12 tones. And an octave is the difference between, I've got some string resonating at that frequency, and then I double that frequency. So if this is, whatever, this is ×2. And that's an octave jump. So they sound kind of the same, just one's a higher pitch. And then you take the range in between these two and you break it up into these 12 semitones. One of the things musicians like to do, especially like jazz musicians, is improvise. And so this thing is called the circle of fifths right here. And it is a way to understand if I'm playing in the key of G. Now that I don't want to get into what that means because we'll be here all hour. But if I'm playing some piece of music in the key of G, how far away from there can I move and still be pretty much sounding okay, like compatible with that key? And so this device here, this circle of fifths, gives us an understanding of a deeper structure that lies within these notes. So let me actually write out the whole 12 tones. So there's A, there's B flat, there is B, there is C, and D flat, D, E, flat, F, E, F, shit, and then G flat, and I'm doing the flats. You can do this with sharps if you wanted, but and then G, and then A flat, yeah. And then it wraps all around again. So how many notes are there? There's 12. And the fact that this thing just wraps around gives me a sense that it might be something like one of our cyclic groups, E12. And in fact, this really emphasizes the cyclic nature of it. It's not the notes in the order. So if you were playing this, it'd be like, I can't get the, so I don't sing professionally. You might be surprised by that, but so check out what this circle of fifths is all about. You don't really need to understand the music or what this is telling us to see what's happening here. So if I started at G and I wrap around, I go 1, 2, 3, 4, 5. Oh, this should be a C. Oh wait, is this the C?
That's the C.
That's the C.
Yes.
Okay,
Yeah.
cool. So that still works. If I go
Yeah.
G, 1, 2, 3, 4, 5, notice that I land on the C. If I move from the C and I go 1, 2, 3, 4, 5, I go 1, 2, 3, 4, 5, I land on the F. So by moving around this circle, I'm actually stepping through this scale 5 notes at a time. And that's called a fifth. And we don't need to get into why a fifth is important or what's useful about that. But in this scale, what are the generators of Z12? So what are the generators? Give me some. What's a generator in Z12? How do we find that? Like it? 1? Sounds good. Anything else? Does 2 work? No, because 2. No, 2 gives us 2, 4, 6, right? 5. There's 2 more. 7. And? Yeah. And 11. Yeah. Exactly. So these are the these are the generators of Z12. These subgroups are all, these are all equal to Z12. So each one of those is actually Z12. Notice that this stepping by 5 gets me through there. So just wanted to correlate the fact that one of the generators of Z12 is exactly the precise step we need to take to hit all the notes that are possible. We want to be able to hit all the possible notes and scales and keys and everything here. So we have to step by 5s. We could also step by 7s.
I was gonna ask.
Yeah, we could. I don't know what that would do. That would be weird, because usually a 7th, when you move up, it's like a little dissonant. Yeah, it's a little dissonant. And so like if you had C and you went up, let's see, so C, so 4. What's that?
So this is all form world. Music world.
Yeah, that's okay. That's okay. It's not going to be on any exam, that's for sure. Yeah, I think like, so if you moved up a 7th from C to 1, well, it's actually not, it's not too bad. Maybe it wouldn't be dissonant.
That's a traditional fifth, like in terms of tones.
Really?
That's a traditional fifth. 'Cause,
That's
like,
7?
Say the cello has a C string and a D string, those are right next to each other, and you play them together, that's awesome.
Yeah, same with guitars too, right? Yeah.
As long as it sounds good, like it.
As long as it sounds good. Yeah, yeah. So, I don't know why. I spent a lot more time looking at this and thinking about it than I probably want to talk about, or your enthusiasm merits, perhaps. Where am I going with this? Oh my God, yeah, I mean, like, this is just like all my, I just spent like an hour just sitting out back the other day, just looking at patterns here. So I don't think I'm gonna go into chord theory and all that kind of stuff. I think we're gonna move on. I just wanted to show you a place where I thought maybe we'd all connect on. And some of us did, some of us didn't, that's okay, and I'll try to bring in some other things that I know so little about athletics. And I
Yeah,
know
that's,
so
where,
little,
that's where most of my knowledge lies.
yeah, and I know so little about what else you know about that I couldn't,
Yeah.
and same for you, I don't know what would, like, I'll try to find some things that like resonate deeply. Like this could have, we did a little bit, whatever. Okay, so let's actually put to use some of our, how did we get those generators? What was the key thing about 1, 5, 7, and 11 relative to 12? How do I know that these are generators? What kind of result? It sure does, absolutely. Yeah, exactly. So the GCD of all these things with 12 is 1. So I can get the order of these groups by taking the order of the big group and dividing it by that GCD, and then that gives me the order of the subgroup generated. I would like you to do something for me here. Would you please find, using the results or looking them up in the book, find all subgroups of Z30. Oh, it's not too bad. It really isn't. Did I even give you your homework assignment? No, because I got all spazzed out about
Yeah, you
these.
did.
Did I?
Yeah, Jesus Christ.
Oh yeah, no, it's you know, things. Terrifying.
He's not strong with us right now.
Yeah, it's not ready for a break.
How you and me both.
I'm gonna come camp out in your cow town. Just nice and quiet there.
You might have to hear the train go off 75 times a day, but.
I won't camp close to the tracks. Like part of my soul, like I resonate with hobos. There's a part of me that I think a lot about hobos.
In the most respectful way possible, I can see it.
Yeah. Yeah, no, it's cool. I appreciate that. Like my wife calls me like her hobo instead of her husband. So, I sing songs about hobos. I'm really into hobo songs.
What is a hobo song?
Oh, don't get him started, Kyle.
Well, I want
Oh boy.
Like Woody Guthrie sang hobo songs. Like back when a hobo was like a thing you could like, I'm gonna be a hobo when I grow up.
That was a thing?
Yeah.
That was a thing.
Oh yeah, yeah. They had a society and everything.
Okay.
Yeah.
Learn something new every day, I guess.
Sure,
Kyle's baffled right now.
Like even the trivial subgroups. That result will come in handy in a bit. Can somebody tell me at least your plan? What is the plan? How do we do this? Besides just like hoping.
I'm just doing that GCD of each of the.
Okay, GCD can play a role. What, like you have a more simple level, like relative to 30, what are the things we're looking for? The divisors, right? Yeah, yeah. So we can get prime factorization of this. So it's going to be 2 times 3 times 5, and I picked a really nice one. What does one of our theorems tell us about divisors of the order of the group? So this is the order of our group. What do we know about a divisor of that order and subgroups? What is the relationship?
Is it like the order over the divisor, the subgroup of?
Yes, yes,
Give or take.
yeah, yeah. So what is it precisely? That's give or take. That's pretty give or takey. What does the result say? It might be on a paper in front of you.
Corollary subgroups of Z.
Yeah, the corollary subgroups of Z, yes. What does the corollary subgroups of Z tell us? Let's put that up here.
For each positive divisor K of N, the set N over K is the unique subgroup of Z of N of order K. Moreover, these are the only subgroups.
That's beautiful, yeah.
Z of N.
This should be D here. This tells us exactly how to find them. And that once we find one of a particular order, we're done. So the orders are all the possible divisors, so we have to think about those. Let's actually start. What is the simplest, smallest subgroup of any group? The tiniest, weakest, lamest.
Lame.
So one here is going to generate the whole group. What is our identity here? I know what you're thinking. What's the identity in this group? 0, yeah. So we've got that super trivial subgroup just consisting of 0 itself. That has order 1. And we don't need to think about that theorem here, but you know. So, what are some other ones? What are some simple ones? I might, if I replaced these, what's the subgroup of order 2? Thank you. So we've got, let's put our order, let's put our subgroup. I'm going to make a pretty chart here in just a second. But so we have order 1, subgroup is 0, order 2, we'll just work our way up, subgroup is 15, order 3, subgroup is 10, thank you. Let's see, so 4 doesn't work, 5, 6, 6, 5, what's the next one up, you think, next largest, order-wise? Seems like 10, yeah. It's generated by 3. Next up, 15, order 15. That is yield 2. And then what about my order 30 subgroup? What's that generated by? So there's my 1 in there, Kyle. That gets me the whole group. This 1 is a generator. Okay. Yeah, yeah. Okay. So, some of these subgroups are contained in other subgroups, and I put this relationship up here. This is written for a general cyclic. How could I translate this to the Z? So this is for a general cyclic. How do we translate that to a statement about Z mod n? I don't have powers, I don't know what G is. We don't even need to worry about like G to a power, right? Because we've got integers that we can use. This should say subgroup here. And again, part of this we don't even have to change. Bless you. What is the relationship between cyclic groups in general and then Z mod n? What goes in here? Could go in here. You're gonna do this. It just comes back to integers. This is a little weaker than the actual statement, but that is a true thing. If I know that this thing is a divisor of this one, then I have containment in the subgroups like that. So, for example, let's take a look here. I know that 2 is a divisor of 6. So what does this tell me? So that means that subgroup 6 is a proper subgroup of subgroup 2. Is that true? This is multiples of 2. This is multiples of 6. So that's true, right? So you get these bigger ones, the bigger generators contained in the one with the smaller generator. So what we're looking for is a tree here, kind of a branched out tree describing all the containments that are possible. And down at the bottom, we're going to have the big group down here. So this is actually Z12. And what we want to do is have what's called a lattice, subgroup lattice in particular. So can you help me, can you make a chain here? Like, can you hook them up? One is the containment. I'm going to draw little lines for mine, just to give you an example of what I'm looking for. So, for example, subgroup 3 is contained in there. Does that make sense? So this is a subgroup of that. This is a subgroup of everything. And this might be asked backwards in some ways. Kind of feels like more should be on top, but let's turn things upside down. Hegemony, is that right? Is that a good word? That's a good word. You probably know it. I feel like everybody in the English department says hegemony like all the time. No? Okay. It's where I first heard it. I get associated with it. I'm gonna make this over here a little bit better. won't have any relationship, like these guys here, right? None of these are contained within the other. They have the elements, maybe some elements in common. What about 2 and 3? Who contains both 2 and 3? 6. 3 and 5. Who's 15? You can kind of see this game here, right? You might not even know what all this stands for, and you can probably start to figure out the rhythm here. So what do we got? We got 6. Oh yeah, the 10, right? So the 10, so that's gonna be a little bit tricky. I'm gonna, yeah, it's a little rough. We almost need like a 3D thing to get this nice, which would be, that sounds really exciting and awesome. What else do I have in here? So I've got, which one am I missing still? The 0, and that's just the base of them all. Does this look good? And this expresses all of the subgroups. The only subgroups, because of that theorem, told me that each of these is the unique subgroup of that particular order. Are there other generators for these subgroups? So like, for example, this one here, are there other generators inside of that group, subgroup? How many? What do we use to decide how many generators there would be? What's that function? The Euler-Phi function. Yeah, exactly. So the Euler-Phi function is going to tell me how many generators there are. If once I know the order of the subgroup, order of this is 12. So other generators, there are a total of Euler function of 12 generators. So this is just the number of integers that are relatively prime to 12, between 1 and 12. And we already worked that through, there's just 4 of those. I also want to point out something here about those subgroups, when we, those generators. So when we looked at this subgroup, gotta show 0, 1, 2, 3. I don't like the way that's written. There we go, much better. Those generators were 1, 5, 7, and 11. Notice that in this group, these are inverses of each other. So whenever you have a generator of the subgroup like 1, its inverse 12, or 11 would also be a generator. So notice that these are inverses. And that's just because if G generates a subgroup, then so does its inverse. We're just seeing that kind of manifest there. What would it mean to have an odd number of generators? How could that happen? How could I have an odd number of generators? Like the Euler function's odd for some values. What would it mean to have an odd number of generators in terms of this inverse stuff? How could that be? This result. make sense or not really?
Or like for, if you have order 1 and 2, then you have one, generator.
Yeah, exactly. I don't even think the Euler function is odd anywhere except for the 1 and 2 that you're talking about, Sydney. So yeah, so it's just those base cases. So if I have a group of order 1, well, that's just the identity. If I have a group of order 2, that's just the identity and one other element whose square is the identity. So it does make sense that I only have one generator, and it's that one. And here it's that one. Okay, cool. Just wanted to have some talks about this stuff. What about this? Can you do this lattice thing for me now with this subgroup? How about C16? Make the subgroup lattice for that, please. This one has a really different look than the other one. Yeah, those are the right. Yeah, yep. This one kind of it's interesting. So let's see what is this. So, this is true, but you can streamline this a little bit to be more precise. Like this is totally right, but this one is also contained in that one, right? So you're not demonstrating all the containments because this subgroup 8 is contained in that one. Does that make sense? So you would want to just kind of put the 4 under this one and then the 8 under that one. And then that still shows you that 2 is contained in there, or 8 is contained in that one. Right, do you see what I'm saying? It's like a little bit of a refinement. So all our factors here, since 16 is just 2 to the 4th, we've got 1, 2, 4, 8, 16. Those are our only divisors. So when I make this little tree up, I'll put the whole thing at the top, just do it in the reverse order. So this is everything that's in there. This has order 16. And then subgroup of order 8 is going to be 2. And that's contained in there. Subgroup of order 4 is contained in here. Subgroup of order 2 is contained in there. And then finally we're down to 16, which is just 0, mod 16. So we just get this straight tree. There's no depth, there's no like branches to it, it's just a little twig. Does that make sense? Yeah? You've got some of this to do. You've got like a little bit of an investigation to do on your homework. Let's do another problem together. Unless any questions on this, we're good. Okay, so this is actually number 37 out of the book. Find all elements of order 8 in Z8 million. Yeah. First off, before we get despondent, how many elements of order 8 are in here? How do we find that? What tool do we use? Yeah, the Euler. Yeah, so I just look at phi of 8. That's literally the number of elements of order 8 in there. Notice how this Euler function does not care about the whole group. It's only looking at those things of a particular order. So phi of 8, what would that be? 4. Awesome. So there are 4 elements of this order 8. So 4 elements of order 8. Cool. And we should be able to crank those out using our subgroups of Zn results. I think the 8 million's there just to like make us realize, make us focus on the things that matter and disregard those that don't. Solid, yeah. That's it. Just add a lot of zeros, right?
Yeah.
Bless you. How many subgroups of order 8 are there in this? Yeah, how many subgroups of order 8? There's 4 elements of order 8, but how many subgroups of order 8? Kyle knows the answer. 4. Are those different subgroups that you've got listed out there?
Not one.
There's 1. That's what that result tells us. We're just like playing the same tunes over and over and over again. That result, the subgroups of Z mod n, tells us that for each divisor of n, so I've got Z mod n, if I have a divisor of n, there's exactly 1 subgroup of order, exactly 1 subgroup of order n over d. So, subgroups of order 8, there's going to be exactly 1 of them, and what's its order going to be? Oh, 8, duh, right, sorry, what's a generator? So Kyle, what did you get for your first one?
1 million.
Yeah, so you took 8 million divided by 8. Just using that result straight up. That gets you the group. It doesn't get you all the generators, but it gives you a good representative. So this is the 1 million group.
It's 10 million.
Is that 10 million?
I think so.
Yeah, thanks.
Too much. Lots of zeros.
Yeah, lots of zeros. And do you see, and I'm pretty sure when Kyle thought of this, you were thinking about Z8, right? And so you just kind of brought it down to thinking about divisors of 8 as opposed to 8 million.
Yeah,
Yeah.
it's a lot easier.
It sure is a lot easier, right? And so the million in here is kind of a red herring, because the other generators are going to be the numbers between 1 and 8 million that are relatively prime to 8 million, and those are going to be 3 million. I'll put commas in there to keep myself straight. That's going to be 5 million. So it's just like if it were 8, and you get 1, 3, and 5, and then 7 million. Is this making sense? Yeah, got that? See, same thing over and over again. Let's push it a little bit further and talk about a subgroup our group we haven't talked about in a while, but we're going to be talking about more and more as we head into the next chapter for sure. So this is problem 78, and what they're asking us is to find a cyclic subgroup of D60. We'll talk about that in a second, but that sounds pretty intense, of order 4. And a non-cyclic subgroup of order 4. So sometimes I look at problems and think about assigning them and think this would be better if we just talk about it alone, or together. So, what is D60? Can somebody help us out with that? Kind of like in like a sentence in an elegant way to visualize it.
One of the composition ones, isn't it?
It is one of the, yeah, absolutely, you're right. What was, yeah, oh, you got it. Yep, sure, yeah, okay, there's this. What was D4? You've done a lot of stuff with that. What did that represent? It was a group of compositions. That was our operation. What were the elements of the group? There's a picture that goes with this, right? Yeah, what's the picture for this triangle? That would be D3. Yeah. Square.
No, you're
Yeah.
sorry.
Yeah. So it's the symmetries of a regular n-gon, right? So this is the symmetries of a triangle. So how many rotations are there here? Right? So we've got this part that's rotations. So we've got R0, R120, and R240. And then we also have what? So they got the rotations, and then what else? Flips. You got flips over each possible axis. So we've got a flip 1, a flip 2, and a flip 3. Same thing here, right? We've got 4 rotations. So I've got this rotational subgroup. And then I've got 4 flips. 1, 2, 3, 4. So I've got 4 flips. And we'd have to define what these flips mean. I'm just kind of being a little sloppy with the 1, 2, 3, 4 here. I don't know here. I'll be less sloppy. 1, 2, 3, 4. There. What's D60?
60
Yeah, so the symmetries of a 60-agon, whatever that is.
Wow.
It's a 60-agon. I guess that's exactly what it is. So this is the symmetries of a 60-sided regular polygon. Regular just means all the angles, the interior angles are the same, all the sides are the same length. Good phrase to know as a mathematician. So what does the rotational subgroup here look like? How many rotations will there be? 60, yeah, exactly. As many sides as there are, we can rotate around. So what is the angle? So here I'm doing the angles. 6 degrees, okay, R6, R12. Yeah, we're not gonna write them out, don't worry. I hope not. I'm not, no. And then what's the last one? Yeah, good. Right on. It is, especially subtracting. So we've got those rotations. How many flips do I have? 60 freaking flips. So flips. Got F1 through F60. We're not even gonna pretend to draw out. I have a feeling any 60-agon I would draw is indistinguishable from a circle right now. Yeah. So we might want one in a bit.
Circle or 60?
A circle that we're gonna call a 60-agon. A circle that for all our purposes is a 60-agon. So how do we find this subgroup of order 4, the cyclic subgroup of order 4? Where do we look? Let's be mathematicians and take this situation and turn it into something that's easier on the mind. What is this subgroup? So this is a rotational subgroup. Can you think of another rotation or another cyclic subgroup that feels easier to work with that acts like this? How many elements are in here? 3. What's a great cyclic subgroup with 3 elements? Starts with a Z. What did you say, Sydney? Yes, thank you, yes. So look, one of our major results says that any cyclic subgroup that you have is either going to be, if it's finite, it's equivalent to Z mod n. So if I have a cyclic subgroup of order n, I can think of this as the subgroup. This is a model for any subgroup of order n that is cyclic. If I have a cyclic subgroup that's infinite, order, what do you think a great model for that would be? Starts with Z, ends with Z, Z. So, that's why we study these things. If you have a finite order cyclic subgroup, it basically is Z mod n. If it's infinite, it's basically Z. And you can make a correspondence between every element here and every element there. Let's take a look at this one here. This is my identity, so it's going to be my identity in Z mod 3. Yeah, what would this one be? What do you think? Is this a generator of this subgroup? Is R120 a generator? Yeah, it is, right? Because 2 of these gets me this, 3 of them gets me this, gets the whole damn thing. Here's a nice generator of Z3. Yeah. And then this is literally twice that one. Right? So I can make that correspondence. What do you think here? What's a great model for this one? Z4. Right? So this is Z4. Here's 0, 1, 2, 3. So I can think of this as the Z part is how many rotations by 90 am I doing? Up here it's how many rotations by 120 am I doing? And that gets me my integer representation. Now this stuff down here we will hold off on because this isn't cyclic. Eventually, we're gonna have everything kind of modeled by Z's, Z-mods, whatevers. Everything's gonna end up being like that. This is gonna be our heart. But for right now, we're just worried about the cyclic part. So what is a great Z model for this one? Z60. So I can think of this, I'm gonna give you a fancy term. A cyclic subgroup of order n is isomorphic. So I use this squiggly equivalent sign here. This stands for isomorphic, and we'll spend a lot of time talking about that. But it basically just means identical to, acts the same, might as well be this. Just different names for the same stuff. So isomorphic to Z mod n. Same thing down here, any infinite cyclic subgroup is isomorphic to Z, no matter what it looks like. I can put a one-to-one correspondence between the elements. So this thing here is isomorphic to Z mod 60. So now, let's just think about Z mod 60 to answer this problem. That sounds better, right? Than like, what, we got a fucking 60-sided thing spinning in my head. That might be good over the break. I don't know what you're doing, you know? But like for right now, we want to get some shit done.
Not bad.
So, what is a subgroup of order 4 in Z mod 60? Forget about the rest of the problem. Think about this. We're mathematicians. What is it? 15, exactly. Okay, cool. Does everybody see how we're getting that? That's mod, that is order 4. And it makes sense, right? 0, 15, 45, 0.
Yes.
So we're back around. Cool. What? Yeah, sorry, go ahead.
So it's part of
Yeah, that was my next question, exactly. So what element in here corresponds to 15 in Z mod 15? If this is 0, 1, 2, 3, Kyle's noticing that you just take that integer times 6, right, to get the rotational, the number of degrees. And really this is 1 rotation by 6, 2 rotations by 6, 3 rotations by 6. Freaking 29 rotations by 6. 59, thank you. 59 rotations by 6. So this corresponds to 15 rotations by 6 degrees. So like Kyle said, it's actually just R90 in this group. Isn't that cool? Like, right? So we're like using stuff. We're not just hoping to hell and scrambling and pulling together. We're being mathematicians, changing this all. So this is our subgroup of order 4. Awesome. What are some other generators of that subgroup? That's one way to write it. That could be tricky. That one might be tricky now that I think of it. Let's see. Let's do. So we've got 60. What is phi of 60? Shit, I don't know. That sounds terrible. I don't even think that's in our little table.
It's not. It only goes up to 12.
Could you look it up for us, please?
Yeah.
Euler just like Euler function calculator, maybe. You know some nerd made one. That has to exist. Nerds have done everything. Nerds basically make everything happen, right? I mean, our people make the world go round. Our people. Yeah, 60, yeah. How many relatively prime? Oh wait, did I, hold on, so sorry, this is wrong. I got it, I'm all jacked up. I'm like thinking of the whole group. We're not thinking of the whole group. We're only thinking of this little dude down here. This is just order 4, right?
Right.
Yeah, so this is actually just Z4.
Oh, yeah, that's.
So that's a lot better.
Yeah.
What's phi of 4?
2.
2. So the other one, I think you were right, Kyle, when you said 270. Yeah. So I think also R270. Exactly. Yeah, sorry about that. Got myself off into outer space there. All right, and we got a deeper problem now. I need a non-cyclic of order 4. It's painful. It's going to become more and more joyfully painful. Joyfully painful, hopefully.
What does joyous pain look like?
I don't know, probably most of your life, I would imagine, right? You like athletics, you suffer.
That's fair enough.
Yeah, there you go.
Working out is right, yeah.
I ripped my toe up, fuck yeah. I'm gonna do it again tomorrow.
I don't know that I hope for that. I think
Well-
it's more of the degradation of muscle and then rebuilding the muscle.
There you go, yeah, constantly suffering to become stronger, yeah. So, what is the order of those little flip dudes? Like any of those flips, what's the order of one of those? Yeah, just, yeah, in particular, just one, so like F1, what's its order? What's the order of a flip? It's 2, right? Because the flip is just around some axis and then flip it back. So those are all order 2. So these things here are all order 2. Holy shit. So each Fi has order 2. Okay. What happens if I put a couple of them together? Is that going to do it? What's a flip followed by a flip? I think it's a rotation. That seems right, doesn't it? Yeah. Let's take a look at our little D chart. Back. Yeah, exactly. That's good. Hey, that's okay. So this is back on page 29. There is the D4 table. And we can gain some understanding, for sure, out of this. So we've got the Cayley table for D4 right there. What happens when you combine a flip with another flip? And you can see the answer right there. Proving that that is the case is a little tricky. I did that earlier this semester for my own jollies, but so flip followed by flip gets me rotation, right? So look at that little lower quadrant of the table. That's where all the flips interact, and each one of those produces a rotation. So the second I put, so let's say I take like one of these flips. Let's just say, okay, we're gonna start off with one of these flips. Let's just say F1, who gives a shit, it doesn't matter. So we're gonna toss F1 into the mix. F1 squared gets me R0, right? So this is F1 squared. I have to toss something else in here. And I have to keep the total order under 4. Right now I've got 2 things. What do you think I should toss in? What happens if I toss in another flip? So let's say we toss in F2. Then that's, I got 3. What's gonna happen when these 2 interact? You got rotation, right? So it's gonna be some rotation. We don't know what, right? But it's some rotation. So when these 2 interact, I get a new rotation that's not gonna be the identity, because that would be where they each interact with themselves. So I've got some new rotation. Oh no. What happens as soon as I've got a rotation in this collection and I'm looking at closure? I'm like interacting all the compositions together. What happens? What if this turned out to be our 18? What has to be in this subgroup once our 18's in there? Yeah, like all the multiples of this have to be in there, right? So once I've got one rotation in there and I want it closed, I've got every power of that rotation. So R36, R54, like, Jesus, like a lot of them, right? So as soon as I've got another flip in there, this thing blows up. So what should I add in? There's some kind of rotation, right? It has to be a rotation. Old flip 1. what could we try, like a safe rotation, you know?
Initial gut reaction was R180, but then you just go straight to the
No, I think that's the right answer.
Yeah.
I do. I think that's the right answer. So let's take a look here. Let's make a little thing for ourselves. There's our 60 gone. Right there.
Oddly like a circle.
Oh, strange. That's weird. I didn't see that coming. So let's toss in R180. And what's the order of R180?
2.
Yeah. So this is order 2. So it times itself just gets me back to here. So now I have to worry, what is flip 1 times R180 composed with R180? So let's label some stuff. I've got my N gone. Let's pick some points on it. Here's A, B, C, and D. So we're going to compose these two. R180, and then I spent, it was a beautiful day to sit out in the shade yesterday thinking about all these things so that I could come in and torment you with them. So when I do R180, let's do that first. That's just going to flip this upside down, right? So here I'm going to keep my flip axis there. So we're going to have A, B, well,
Shouldn't A be in the bottom left?
yeah, they're backwards, right? Is that, wait, what's fine?
So A is in the bottom left.
Thank you. Oh, thank you. Okay, B, C, D. So yeah, we didn't change any orientation, so everything still flows in the right order. So there's that, and then I do a flip over my axis, and that's going to change orientation. So let's do flip 1, and then let's C, D, B, A. Is that equivalent to anything we already have? So if this is something new, we're screwed. Because right now, we've got our 4 elements, that, and hopefully just this product. Is this equivalent to something we already have? It freaking better be. Let's take a look. Let's actually map out what we have. So this is, let's just do flip 1 on that. What would flip 1 look on our original state? Like this? Yeah. See, like that. Huh. What the hell is that flip 1? I don't know. This should work out. I had this one. Like one. See? What were you saying, Kyle?
Flip 15, whatever is directly horizontal.
But as soon, oh, I see what you're saying. As soon as we put another flip in, then we've got too many elements. That's the problem, right? Because we want 4 things in here.
I don't see how you,
Yeah.
how in the world do you rotate that to get, because the elements change.
Can you explain what you're saying a little bit more?
Like, I don't know how you go from that, or from the far right back to that.
To this, to that,
Yeah.
or yeah. Yeah, I don't, yeah. Let's see, so did I do it right?
Because you pull, it doesn't matter how many times you rotate that around, the
Yeah.
B's always gonna be on the wrong side of the A.
Mm-hmm. What was happening on my patio yesterday? Here, let me put my pictures up here, because I had this worked out, and I convinced myself that this works. So let me draw my new pictures, and then maybe we can pick them apart, find if I did something wrong. Okay, so I started with yield circle, so here's my base state. Oh, here's what I did. This might actually help. So I've got A, B, I think this is gonna help, I think the way I set this up. So this is R naught, this is my original state. And then if I do R180, and let's say we're gonna do it counterclockwise. So R180 would look like this. Not really, yeah. Oh, thanks, Kyle. Yeah, yep. So it's just A, C, B, D. Did I do that right?
Yeah.
Yeah, okay. Cool, so there's R180, and then let's look at flip 1. And so our flip I think I know what's going on. So our flip is going to fix 2 points, and that's the problem with my original picture. So let's say this is my flip. And we're just picking a couple points on that flip that aren't gonna change, they're gonna stay fixed. So after that flip, we've got A, C, and D, and D. They maintain their current position. Now we can think about what happens when I do first R180 and then do a flip. So when I do this, R180 followed by a flip. That flip is this flip right here. It's that vertical flip, right? So what am I gonna have? I'm gonna have D fixed, I'm gonna have B here, and then I'm gonna have A and C, like that. Is that correct? Yeah. Cool, so this is a new element, and that's okay that it's not that. But once I apply this, so when I do R180, flip one, so now apply R180 to that, I better get that one, and I think that I do. Yes, yeah, I think it worked out. Cool, so what we've got, what we can see here is that R180 flip one is equal to flip one R180, and we can call that fourth element anything we want, but now we've got 4 elements. We've got R0, R180, flip one. Oh, was that Kyle? Sorry.
No, I was talking to myself.
Okay, it's all good. That's okay in this place. It's a safe space for all sorts of things. So that would be our subgroup of order 4. And I think that's going to be the case no matter what. You just have to make sure that this flip has to go through 2 of the nodes you're actually keeping track of there. That was what I screwed up over there. And it's not cyclic. You have to like that you're getting into this.
It would work up there too.
Would it?
Yeah, you plug your own into the top left, you get the one on the far right.
Oh, okay. Awesome. Okay, that's good. That's good shit. For some reason, this was confusing me. You're saying if I apply 180 to that thing up there?
Yeah, you'll get through that.
Oh yeah. Okay, it did work out. I don't know why it got so confusing, because it is confusing, I guess. Algebra. Yeah. Let's call it a day. Sound no good? I'm not going to. Now I know you all love to come to my office hours and hang out, but I'm not going to have them tomorrow. So you're just going to have to find somewhere else to go. Okay?
What time are you?
Yeah, exactly. Yeah. Shit, I don't know, like 2 to 3:30 or something. They're on Zoom, but they're not going to be tomorrow because I'm going hiking.
Darn it, I'm really hoping it pops in tomorrow.
I'm done. I'm starting my break. Yeah.